Hello and welcome back. In this, so far in this series of videos, I talked about linear Kalman filter, the concept behind it, and I tried to explain it not from a mathematical point of view, the way that to be understandable, and you guys can implement it without getting involved with the mathematical concept behind it. Also, we talked about unscented Kalman filter. We talked about adaptive unscented Kalman filter and what is its advantage and where it can be useful for your case, for the case you are working with. Also, I talked about the physics-aware, the objective function we define to optimize the hyperparameters of the unscented Kalman filter or adaptive unscented Kalman filter or any type of Kalman filter you are working with. In this presentation, I'm going to show you one case study that we used the physics-aware objective function or physics-aware objective function to identify its states, its parameter, and the reason we chose this case study because it was toward the project we have with the Hydro-Quebec, one of our industrial partners, and we want to develop a digital twin for hydro turbine. This is the schematic of the hydro turbine, and in this hydro turbine, usually people they are able to measure the vibration on 2 or 3 locations. For example, I showed 2 of them, the bearing locations. Usually, they measure the vibration in X and Y direction. Usually, the shaft of the hydro turbine is very long, almost 10 meters. Then you are measuring the vibration in a very sparse. Then you have a sparse sensor. You see, you are only measure the vibration on 2 or 3 locations in X or either X and Y or both of them. One of the questions that people at Hydro-Quebec are asking us is that if you measure the displacement of vibration in X and Y direction, can you use this displacement of vibration and estimate the force acting on the bearings? Why force? Because force gives you more information about the actual situation of the bearing and loading condition and the loading condition of the hydro turbine. While if you just rely on the displacement, it's more kinetic and kinematic and local information about the system, and it does not give you the actual behavior about what's happening inside the system. At the other side, usually it's really hard to install strain gauge and different type of force sensors at the bearing to measure the force directly. Then that was the reason they asked this question, to see if we can use displacement of vibration and reconstruct the bearing reaction forces. Because in the Hydro-Quebec, they didn't have any any unit that they had installed the force sensor beside the vibration sensor to have the force and vibration at the same time and validate the reconstruction we are going to do. We decided to collaborate with the Vattenfall Research Development Center in Sweden, because they had a vertical axis shaft here. This is a 1 meter shaft. They had the rigid shaft installed with a motor to rotate the shaft, and they installed both the vibration sensor to measure the displacement. For example, I'm showing the displacement of vibration in the lower bearing. At the same time, they measured the reaction force of the bearings. It was a tilting pad journal bearing. I don't want to go into the detail here for you. You can read all the details in the paper, are well explained. Then we decided to go with this lab scale experimental setup and see if we can use the displacement of vibration and reconstruct the bearing restoring force. First of all, let's look at the basic equation. Usually we know that this is the force displacement relationship. For example, force is, if I got it right, simple force is equal to Cx dot plus Ky. This is the restoring force in the bearing. Yes. Then for this system, because we have the force in 2 directions and the stiffness and damping in 2 directions, we write it in a matrix form. Then the thing is, for each bearing, we measure the displacement in the X and Y direction. Then we are interested to reconstruct the F, X, and Fy for each bearing. But we measure these 2 things. We don't know what are K value in each direction. We don't know what is the damping value in each direction, and we don't know what is the displaced velocity of the vibration in each direction. Then we need to have all these 3 blocks to be able to reconstruct the force. Okay, then we were thinking that here we can use unscented Kalman filter to estimate and estimate the states and identify the parameters and solve this problem. Then first of all, we had to to find these K and C, we need to define a model here. Then we wrote the equation of the motion of this vertical axis shaft. We assume the shaft is rigid. Then this is the equation of the motion considering the gyroscopic effect of the shaft. And because we assumed the shaft is rigid, then we were able to write a relationship between the displacement at both and the displacement of the center of the gravity of the shaft. And you see, this is the measurement function we have, and in addition to the displacement in the x and y direction, we consider the rotation of the shaft along the axis x and z. And this is, for example, the K matrix. As you see above, we wrote the K matrix here based on the short bearing theory, which I don't want to go into the detail here. And similarly, there is a CB matrix also, and you can read the information in the information you're looking for in the data. After that, we transferred this equation into the state space form. Then that was the stage we had to find the hyperparameters. For this study, we didn't go with the standard x hat k plus 1 minus model, the transition function. What we did, we divided the whole the whole physics by the transition function. Why? Because we were interested to estimate the displacement and stiffness value and damping value. There is a big difference, scale difference between the displacement and the stiffness value. And to normalize everything, all the states in the state vector, all the quantities of interest in the state vector, we divide all of them by the measurement function to scale down the loss function and make it easier to calculate the loss function. And the reason I showed you this loss function here is that you can play with this loss function as much as you like, because it's kind of similar to the loss function people are these days using in physics info neural network. Then for your loss function, you can play with it and keep it and write it in a way that suits your case study. And this is another advantage of these physics aware of the physics aware loss function we define for unscented Kalman. Then based on this physics aware loss function we defined, we optimize the hyperparameters, and we identify the stiffness and damping value of the upper bearing and lower bearing at two different states. You see here, and as we expected, based on the gyroscopic effect, the stiffness value at the higher RPM is more than the lower RPM as we expected to see. And these are the damping values we estimated for two different speeds, for upper and higher and lower bearing. And using these estimated states and parameters, what we did, we reconstructed the bearing reaction force. As you see here, the blue dots you see are the measured value, and the line you see here is the estimated or reconstructed force value. This is for the 1500 RPM, and this is for 2000 RPM. And as you see here, for 2000 RPM, the bearing reaction force is more than 1500 RPM, and this is exactly what we expected. Using this case study, my goal was to show you that how you can use the concept we talked about for lab scale experiment, lab scale study. Okay, now I showed you this case study, and I'm gonna stop my presentations here. But there are many questions that still needs to be answered if you want to implement unscented Kalman filter or adaptive unscented Kalman filter, Kubacher Kalman filter, ensemble Kalman filter, which I didn't talk about it yet. But in general, I'm gonna bring your attention to one main question. Maybe you can think about it. Mx double dot plus Cx dot plus Kx equal to Ft. For all of these case studies, for joint state and parameter estimation, I assumed I know the Ft. I assumed I know the mass. Yes, usually I assume I don't know Cx dot or Kx. And this is what I measured usually. Yes. My question here is, what if we don't know Ft first? Ft is unknown. This is a joint input state parameter estimation problem, which we talked about in our paper. Then you can go and read about. The second case I'm going to talk about is I'm not going to talk about it. I'm going to bring your attention, and maybe you can read it in my papers. Is number two, we said that we can use adaptive Q&R. Can we quantify the modeling uncertainty and measurement uncertainty using these adaptive techniques or not? For example, you do a simulation study, you impose noise to your measurement to generalize the problem. Using this adaptive R, are you able to quantify the noise you impose to your simulated measurement or not? Then quantify Q and R. Can we do that or not? And the third question I'm going to ask here: what is the limitation of number of states and parameters we can identify using an Unscented Kalman filter? For example, we solve the problem for a 3-degree of freedom system. What if we have a 10-degree of freedom system, 20-degree of freedom system, 50-degree of freedom system? Then, as I said, for a 1-degree of freedom system, linear 1-degree of freedom system, we have 2 states and 2 parameters. Then, if we have 10, it means we have 20 states and 20 parameters. If you have 20-degree of freedom system, we have 80. We have 40 states and 40 parameters to estimate. I'm telling you, using the Unscented Kalman filter, it's really hard to estimate 40 parameters. Then how can we solve this issue? These are some open-ended questions. People are still working on these. And if you are interested in Unscented Kalman filter or in general, any type of Kalman filtering technique, you can work on it. And the last question I'm going to ask you here is, can we replace prediction part with a reduced order model or non-physical model? This is the first question I ask you. Then, for example, you have a bunch of data from a system, but you cannot write down the physical equation. Can you use the data, develop a reduced order model, and use that reduced order model for model prediction and update your reduced order model parameters based on the coming data? Or use a non-physical model like LSTM or neural network or whatever. These are the open questions that still people are working on using different type of Kalman filtering. I'm gonna stop here my presentation, my video. Feel free to contact me if you have any question. I put my email, all my papers in the description. I would be happy to have your comments, your questions, to talk about it. And that's all. Thank you, and good luck.